In this video, we're going to be talking about integration through approximation. And the real, if you really look down at calculus, it really breaks down into two main subjects. And one is, what we've been doing, differentiating, which is where, we look at a curve like this and we're able to find the slope at any given point, here, over here, over here, and so on and so forth. And that's just the differentiation part of calculus, taking the derivative. But the second part of calculus really consists of integrating. And in other words, that means finding the area under a curve. When we've been thinking of areas in the past in geometry or algebra 2 and so on and so forth, we've been dealing with, nice shapes like squares or, triangles, so on and so forth, things we already know. But if I gave you this curve, the one that's on the screen right now, and I said, hey, find that area, well, how would we tackle that? How could we find the area that just encompasses, all of this? And the answer is you can't without calculus. It's simply impossible. So before we can introduce the idea of the integral, though, it helps to first understand where it comes from. And this is often how many calculus books will start you off, and hence why I'm covering this subject. So remember that, with derivatives, we first had to learn the limit of the difference quotient and so on and so forth in order before we could use the shortcuts. The same rules apply for integrals. We first have to learn how to approximate and use the long way before we can come to appreciate the shortcut methods. So the first idea is that if I want to find the area under this curve, want to find this, I have to break it up into rectangles. And if I break it up into rectangles like this, let's say I break it up along these lines or something like that, then what's happening is, I can compute the area of these rectangles, right? If I break it up into these rectangles, then I can compute the area of all of these rectangles and then add them up. And that area, it's just simply, length times width. So I would do just length times width of each of these rectangles, add them all together, and that's my approximated area. But then you see this, I'm doing this, and then you say, well, what about, this area right here? We're not including that. And I would say, okay, well, you got me there. So let's try. What if I added more rectangles? Maybe, I did it this much. I did this. I did it like every little sub interval. And excuse, these rectangles are terrible. If you can see here though, like if I just kept doing this, I just kept breaking down a little tinier rectangles, so on and so forth, tiny little slivers, then you see that this area gets less and less. And the idea is that if I keep taking, if I keep splitting this up into infinitely many rectangles until it's like even smaller than that, there's barely any distance between these rectangles, then I'm going to be able to get the actual area under this curve by dividing all this whole region into infinitely many rectangles, and that's the idea. So the first part, if you're working with the Stewart Calculus textbook, it'll often ask you to approximate the area by using a certain amount of rectangles. And before we can do that, let's really just let's really discuss some of the formulas you'll need to know. So oftentimes they'll always give you an interval. There's always an A to B. This is the starting to ending, and I've labeled it here, from 1 to 2 with these blue lines. That's usually the interval. Um, there's delta x, which is simply b minus a over n. And that's simply the ending interval minus the starting interval over n. And n is the number of rectangles. So n is the number of rectangles. So number of rectangles. And it'll often ask you to use right or left endpoints or even the midpoint. And you might be thinking, well, what does that mean? Well, think about this. This delta x right here, this basically is the width of each rectangle. So if I had a delta x of 0.2, well, this rectangle would be like this. If I'm going to use right endpoints, that means the top right corner of this rectangle is going to intersect this graph. So it's going to go like this. And what that means is we're going to be using, in this case, f of 1.6 as our height. So this would be our height right here, f of 1.6. But if I was using, left endpoints, then this 1.4, the top left corner, would be intersecting this graph. And you could see here that I get an over approximation as well, and that can happen as well. So I get an over approximation, so then I would be using the top left corner. That would stand for my height, not this. So f of 1.4, whatever this value is, that would be my height, not this f of 1.6. And if I was asked to use the midpoint, if I was asked to use the midpoint, then I would just pick some value in the middle, some value right in the middle of this rectangle, and that would stand as the height. So what it means, left or right endpoints, that's basically what determines your height. That's what your height is, simply. So, and delta x is simply just your rectangle. So I'll keep that in mind. So over here, f of x, and since this can change, I can use right endpoints or left endpoints or midpoints. I'm going to call this f of xi, where this xi means any point. It can be right, left, or middle. So this is basically our height. It's our height right there. And then this delta x is the width. And that's all we really need for a rectangle. We just need the width and the height, and then we just add it all together. So the general formula is that you simply just do delta x times f of, let's just say x1 for the first rectangle, plus delta x times f of x2 for the second rectangle, plus delta x times f of x3 for the third, and so on and so forth. And you would just keep going like this. But there's a more compact way to write this. And the better way to write this is you can actually just factor out this delta x. You can factor out this delta x right here. And you would leave it as delta x times f of x1. And again, this I right here, this basically means that we're using the right endpoints, left endpoints, or midpoints. And it also means that this basically stands for the number of the rectangle we're using. So f of x1 plus f of x2, and so on and so forth. Where this delta x is the height, and these f of x values, or sorry, delta x is the width, and these f of x values are the height. So let's just try a really quick example. Let's try an example, and we'll just see how we do. And obviously, they're going to give you the function, and they'll always give you the amount of rectangles you're supposed to use, and they'll give you the interval. So a lot of the work is already done for you. You just got to know how to do it. And this is really a really easy section. There's no calculus involved. So it's as long as you're comfortable with algebra, then this should be fine for you. So let's say I was given f of x equals 1 over x from x equals 1 to x equals 2. Okay. And also it's going to give me n equals 4, where n is the number of rectangles, and it's going to tell me to use right endpoints. Right endpoints. Okay, so the first thing I want to do is when I see these is I want to compute my delta x. That's always the first thing you always want to do when you see these types of problems. So remember that delta x is b minus a over n. And this is simply going to be 2 minus 1, because 2 is the second value in the interval, and 1 is the first value, so 2 minus 1 over n, where n is the number of rectangles, so 4, and I'm just going to get 1/4. 1/4. Okay, and now we basically need to figure out what these endpoints are. And there's two ways to do this. And for this one, I'll show the graph just so you can kind of see. So I have the graph right here, and let me just kind of put it right about there. Okay. So what I want to do in this case is I want to label what these endpoints are. So we're starting at 1, and that's perfect because, that's our starting interval. So that's this blue line right here. And then we want to go over 1/4, or, 0.25. So our second rectangle would look something like about right here. And let me just kind of sketch this. It's a pretty bad rectangle, but it's fine. So there's 1. So this is about 1 point. That's about like a 1.3, but it's close enough. Okay, and then basically we would just use all of these little values, and I don't want to draw rectangles over and over again because you'll get the point. But what we have to do is we're basically going to need to show what these endpoints are. And so you'll basically just want to start at 1, and then we're going to want to go over 1/4. So we're going to go to 1.25, which is about, right here. So I'll label 1.25. And then we go over 1/4 more, so 1.5, another 1/4, so about like 1.75, and then another 1/4, and then we'll get at 2. So if you do that, then if you draw your rectangles, they'll be at these points. So it looks something like this. And again, these are just really bad rectangles. Don't even try to copy this. It's really hard to draw on this drawing pad, but you get the picture. So let me show you how to do this if you didn't really know the graph, if it wasn't really as obvious to you. So what you would do, and this is a method that I like to use as well, I think that it makes it a lot easier, is I don't really worry so much about the graph, but I just really I plot a number line, just a little number line. And so, okay, well it says from x equals 1 to x equals 2, so 1 to 2. And then our delta x is 4, and your delta x is basically how far you go over each time. So we're going over 1/4 or 0.25. So I'm going to go to 1.25, and then to 1.5, and then to 1.75, and then to 2. And so now we have to know which values to pick. And since we're using the right endpoints, the right endpoints, then we want to pick basically all of the values to the right in each of these subintervals. So, right here, this is a subinterval. This is a subinterval right here. This is a subinterval, and this is a subinterval. And you can see they're little rectangles even. So I want to pick, essentially for my right endpoints, I want to pick this guy, this guy, this guy, and this guy. So I'll do exactly that. So I'm going to get, remember the formula, it's delta x, and then, f of x1 plus delta x f of x2, and so on and so forth. But remember, we also said that we could press that down if we just factor out the delta x, and it's f of x1 plus f of x2, and so on. So I'm just going to apply this formula right here, and it's really not even a formula if you think about it. It's really just you're really just taking the area of a rectangle. So my delta x, in this case, it's 1/4, and f of x1, that's simply just, you're simply just going to be plugging in those endpoints. So 1.25 plus, or sorry, you're going to plug your endpoints into the formula. So f of 1.25 plus f of 1.5 plus f of 1.75 plus f of 2. And now what we're going to have to do is we're going to think about what f is. Well, f is this function up here. Remember, f is equal to 1 over x. F of x equals 1 over x. So my last step I'm going to want to do is I'm going to want to just plug all of those values in. So 1/4 over, and remember, f of x equals 1 over x. So I'm going to use 1 over x, and I'm just going to plug 1.25 in for x. So 1 over 1.25 plus 1 over 1.5 plus 1 over 1.75 plus 1 over 2. And then if I plug all that into the calculator, I'll get some value that's about 0.63452. So 0.63452, and that's about the area under the curve over this interval. And this, again, this is just an approximation, since obviously, these are pretty big rectangles and we're only using 4 of them, so that's not even, that's not even close to what the exact amount is. So okay, now let's do the same thing. Let's do the same exact thing, but we're going to use left endpoints. And let me just box my answer over here. Okay, so let me write it over here. Same thing, but with left endpoints. So let's use the number line method. And again, you can use the graph if you want. Again, I encourage that even because you can see the bigger picture better. And again, if it's left endpoints, then you would just draw a line straight up from, from the values. Since we're using the right endpoints, I would draw a line straight up from 1.25, from 1.5, from 1.75. But again, it's up to you. So okay, well, my delta x is going to stay the same actually. So remember, it's b minus a over n, and my b value was just 2, and my a was 1. So 2 minus 1, and we're using 4 rectangles. So your delta x is going to stay the same. Your delta x is going to stay exactly the same. And let me just draw this number line again. And remember, we're starting at 1 and we're ending at 2. So we would go to, 1.25, 1.5, 1.75. And now we're using the left endpoints though. And remember that each of these little subsections is its own little interval. It's its own little rectangle. So I'm going to pick the left part of each of these little subsections. So this one, this one, this one, and this one. So you're picking the left one because this is a subsection, this one, and this one. So I'm picking the left side of each of these. So 1, 1.25, 1.5, 1.75. So now let's just work all this out. So my delta x is 1/4. And remember, it's f of 1 plus f of 1.25 plus f of 1.5 and so on and so forth. So I'd get 1 over 1 plus 1 over 1.25 plus 1 over 1.5 plus 1 over 1.75. And I'm not including the 2 because I'm using the left endpoints of each of these little sections. So I'm not including the 2 here. And this is going to be approximately 0.75952. And that's our answer. So pretty easy, I obviously didn't need as much time as I did to explain this. I just really wanted to be thorough about it. Honestly, this isn't really much calculus work, but it might be a little confusing to wrap your head around it first. So let's just breeze through one more example, and this video might be a little longer than I anticipated, but that's okay. So let me clear the board really quickly. So let's say I had now f of x equals 1 plus x squared, and my interval is -1 to 2, and it might say from x equals -1 to x equals 2, that's fine. And I'm working with 6 rectangles, and I want right endpoints. So right endpoints. Okay, so let's begin. So my delta x, remember delta x is always what you want, b minus a over n, so 2 minus -1 over 6, that's going to give me 3 over 6, and that's going to give me 1/2. Okay, and now let's just draw the number line really quickly. Again, the number line is just the fastest way in my opinion. So I'm starting at -1 and I'm ending at 2. And then I need to determine where to put each of my little tick marks. So from -1, I'm going to go over 1/2 because that's my delta x. So -0.5, just adding 1/2 to this, and then over another 1/2, and then over another 1/2, and then over another one, and then over one more. Okay, so now I just have to determine which ones I'm going to pick. Well, I'm using the right endpoints of each of these little subsections. So I'm going to pick this one, this one, this one, this one, this one, and this one. So I'm picking these 6 right here. So now let's just put it all together. So my area, it's about 1/2 and then times, well, 1 plus negative 0.5 squared. Again, remember it's f of x1 plus f of x2 and so on and so forth. Well, my f function here is 1 plus x squared. So I'm just plugging negative 0.5 into 1 plus x squared. I'm plugging negative 0.5 in for x. So plus 1 plus 0 squared now, plus 1 plus 0.5 squared, plus 1 plus 1 squared, plus 1 plus 1.5 squared, plus 1 plus 2 squared. And again, I'm not including this negative one because I'm using the right endpoints. I'm using the right endpoints of each one. And if you put all this in your calculator, you'll get that this is approximately 6.875. And that's your answer for that one. So if you're using the right endpoints, you're using the right endpoints there. So now, let's make our approximation a little different, and let's use the left endpoints. So let's do left endpoints now. So left endpoints, and everything else is going to stay the same. Everything else is going to stay the same. So my delta x, it's still b minus a over n. It's going to stay exactly the same. And it's 2 minus negative 1 over 6. So 2 minus negative 1 over 6, and that's going to be, just 3 over 6, and that's going to be 1/2. So same thing as we did before. And we're running from negative 1 to 2. So we're running from negative 1 to 2. So I'm just going to draw my number line one more time. So negative 1 to 2, just like we did up here. And we're going over 1/2 each time. So negative 0.5, 0, 0.5, 1, 1.5. So now we just have to use our formula. So 1/2. And now we have to pick which points we're going to use. Well, we're using the left endpoints. So again, look at these little subintervals. I'm going to use this one, this one, this one, this one, this one, and this one, and not the two because I'm using the left part of each of these little subsections. So my function, it's 1 plus x squared. And let me write that over here. Same as before. So it's going to be 1 plus negative 1 squared plus 1 plus negative 0.5 squared plus 1 plus 0 squared plus 1 plus 0.5 squared plus 1 plus 1 squared, and then plus 1 plus 1.5 squared. And now if you plug all this into your calculator, you would get the value 5.375. And that's by using the left endpoints, And before we were using the right endpoints. So you could see that our answer is a little different, and it was like that in the example we did before. And so you're going to notice that, when you use right endpoints or left endpoints or midpoints, your answers are going to be a little different. And it's up to you to determine, which one's the best approximation. And it's usually the midpoints that are. So now let's change this up a little bit and use midpoints. So again, my delta x is going to stay exactly the same. It's going to stay exactly the same. So my delta x is 1/2, just as before. And we're still running from negative 1 to 2. And n is still 6. We're still using 6 rectangles. So now let's just draw that number line. So I'm going to draw the number line from negative 1 to 2, negative 1 to 2. We're going over 1/2. So again, we're doing this one more time. So 0, 0.5, 1, 1.5. So we're looking at the midpoints, and we have to pick, well, which values am I going to use? Am I going to use this one or this one? Well, those were endpoints, remember, because all of these were little subintervals. These were little sections. So I can't use the, if I was looking at this, I can't use the 1 or the 1.5, or if I'm looking at this, I can't use this guy or this guy because those were the endpoints. What I want is the midpoint. I want the value that's directly in the middle. So I'm going to pick this part right here. I want the value directly in the middle. And what happens to be directly in the middle is simply just negative 0.75. You'll literally just take these numbers, you add them together, and you divide by 2. You just take the average of these two numbers to get their midpoint. And if I want to look over here, it's negative 0.25. And over here, it's 0.25. And then I get 0.75. And then I get 1.25. And then I get 1.75. Okay, so now all I have to do is I just plug this into my formula. So I get 1/2, and then 1 plus, well, what was my formula? It was f of x equals 1 plus x squared. I'll write that over here. So 1 plus negative 0.75 squared plus 1 plus negative 0.25 squared plus 1 plus 0.25 squared plus 1 plus 0.75 squared plus 1 plus 1.25 squared, and then plus 1 plus 1.75 squared. And if you put all of this into your calculator, if you put all of these computations in your calculator, you'll get the answer. This is about 5.9375, and that's what our area approximately is. So again, these answers are all a little different, and it's usually the midpoints that are the most accurate. But, books will often ask you to do all 3 of these tests, and they might first ask you to do, n equals 4 first, and then n equals 6. They might ask you to do less rectangles and then more. Obviously, the more rectangles you have, the better your approximation is going to be. And that's really all I have to say on this topic. Again, this is pretty simple if you know how to do it. This video is mostly just teaching you how to implement this. Really just remember the delta x formula, and if you can even make this number line and sketch the basic graphs, then you should be completely fine. And again, I apologize for not sketching the graphs more. I just didn't really think it was relatively important to this video. Obviously on a test you might be asked to graph it, which in that case you just make a rough sketch, and whatever your endpoints are, if it's asking you to use right endpoints, then you just draw lines straight up from your right endpoints and then connect them or something like that. If it was your left endpoints, then you draw lines straight up from here. You'd basically do like this or something. You do like that, I don't know. And if you use midpoints, then you just kind of draw a line straight up from there until you touch the curve, and then draw your rectangle from there or something. But that's really all there is to it. So hopefully this helped a little bit. And again, if you have any requests for any videos you want me to record, feel free to send me a message and I'll do my best to respond. Anyways, thanks for watching.